Hey guys, welcome to my video on implicit differentiation. And this is going to be an advanced differentiation technique that you would see typically after at least the chain rule, because it is going to be kind of an integrated process with implicit differentiation, along with other, normal differentiation rules like the power rule, the product rule, the quotient rule, things like that. So, as you can see, there's definitely going to be times in an algebra class or in a math class or something where you're going to have an equation where you can't just disregard y. It has to be considered as an input value also, kind of like x. And if I need to find the derivative of that, because we have two variables at this point, we are entering the realm of what is known as implicit differentiation, where we're going to take the derivative of something with the respect to something else. And that's kind of what we're seeing here. We are taking the derivative of something, in this case the derivative of y, with respect to x. And that's what we're seeing kind of down here. The derivative of y with respect to x is often just written as, this thing right here, dy dx, or dy over dx. We just call it dy dx. But I typically am going to get lazy and say dy dx is just y prime, and I'll show my derivative that way. So here, on the right, d dx with respect to x, that's just like when I take the derivative of 1x, that's just 1. That's why it goes to that. Now we do have, in some cases, where we're going to have to apply the chain rule for y. So for instance, if I just look at y by itself, the derivative of y would be 1, but I have to multiply, that's the derivative of the whole thing, but I have to multiply it by the insider part here, which would be y prime, or dy dx. That's kind of how the chain rule is going to be used when we use implicit differentiation. That's not the only way, but that's a way that we're going to be looking at the chain rule. So again here, the notation shows you in the numerator what you're deriving, and the denominator shows you what you're taking it with respect to. Typically the denominator is x. Sometimes the denominator is t if you're doing like a related rate or something where you're having to do it in terms of time. But here's a typical process of what we're doing. But if you have it in your notes, great. If not, you might want to write it down. But this is essentially just everything that you've been doing in algebra forever. Isolate a variable and tell me what is it equal. So we take the derivative of everything, whatever we have, with respect to x. Anywhere I have dy dx or y prime, we isolate it, get it on one side of the equal sign, and then if I have to do any substitution, then I do any substitution to actually show what the value of that is going to be. And that's kind of what we're doing here. We have this equation, x times y plus y is equal to 8, and it's asking us to evaluate it at the point 3, 2. Now, looking at the equation itself, when we are looking at this, we should be able to recognize that this guy right here, because it's the product of x and y, that here I'm going to have to use the product rule. The product rule when I take the derivative of that. Now, I'm going to go ahead and just kind of write it out here again, just x times y plus y is equal to 8. So take the derivative of everything. So we're going to take the product rule here. So I'm going to leave x alone, and the derivative of y, I'm going to write it as y prime. Then the sum, so the derivative of x is just 1. So if you want to write the 1, you can. And we leave y by itself, so that would be 1 times y, or just y. And again, we're kind of using the chain rule on the y itself, but the derivative of the y would just be y prime, and the derivative of the constant is 0. Now, again, depending on maybe where you see it, when you see it, who you see it from, maybe what you're seeing, and I'm going to just write the same thing here in a different color, x times y plus y is equal to 8. Well, again, I'm still using the product rule here, but the way that I might expect to see it written would be x times the derivative of y with respect to x, dy dx, plus 1 dy dx. Or, nope, I'm putting that in the wrong spot. Plus y, 1y, and then plus here, dy dx, to be equal to 0. So this is, on the right in blue, that's probably the most conventional way of writing it, but when you have a lot of these things where you're having to work them out, taking the time to write dy dx, dy dx, dy dx over and over and over again gets really tedious. And that's where I'm saying I get lazy, and that's why I'm using the prime notation kind of on the left. So I'm going to finish working out the problem on the left. We want to get the y prime terms by itself. So if you notice, I have a y prime term here and a y prime term here. We're going to treat that as a common factor. So I'm going to factor out y prime from those two terms. So giving me x plus 1. And I'm going to go ahead and move the y term from the right side to the left, or the left side to the right side through subtraction. So that'll just be negative 1y. Now we just want to get y prime by itself. That's the variable that we're interested in. So divide everything by the x plus 1 expression, and I'm going to get negative y over x plus 1. Now at this point here, I'll kind of go back to the, to the blue stuff on the right. Once we had, so here it would have worked out to look like dy dx is equal to negative y over x plus 1. So the typical notation to show how we're going to evaluate it at this point is we would say dy dx, where we're evaluating at 3, 2. And then you do your substitution where I'd have negative 2 over 3 plus 1. That's kind of the typical notation of what you would see. But again, I get lazy. I'm going to just do my substitution at this point. I would say y prime would be equal to negative 2 for y and 3 plus 2, 3 plus 1 in the denominator when I substitute the 3 for the x. So that's going to give me negative 2 over 4, or negative 1/2. So a lot of times what you would be doing, really, a lot of times you would stop here when you're doing implicit differentiation. Just what is y prime going to be equal to? But in this case, because they gave us a value at which to evaluate it with, a point for x and y, that's why we're continuing on. But a lot of times with implicit differentiation, you're just taking the derivative of the function with respect to x, and you're isolating whatever dy dx would be. So here, this is where I would encourage you to go ahead and try pausing the video and working it out, but this one's going to be just a little bit more complicated as far as what we're going to be seeing. Of course, here, the x times y, again, this is an indication where we're going to be using the product rule. And here, where I have the 2y squared, this is going to be a clear indication where I have to use the chain rule. Okay, so let's go ahead and work this one out and just see what we get. And I'm not going to do the dy dx whatever. If you want to do it on your paper, that's great. But I'm just going to stick to the prime notation with y prime and so on. So I'm going to just rewrite the problem here real quick. X plus 3 times x times y minus 2y squared equals 2. And of course, we know where we're going to evaluate it in. So we want to isolate take the derivative of the whole thing, isolate y prime, or dy dx, however you're writing it, and then do the substitution to actually tell me what is the value of y prime at that point. So the derivative of x is just 1. Here we're going to use the product rule. So I'm going to get x times y prime plus 1y for the product rule, just like what we saw in the last example. And here we're going to have to use the chain rule on the negative 2y, or negative 2y squared. So the derivative of the whole thing will be negative 4y. The derivative of the inside part is just the y value itself, so that would be y prime to be equal to 0. Now we want to try to get y prime by itself. So you can see we have y prime in 2 places. So I probably should have distributed the 3x or left it there. But let's go ahead and distribute 1 plus 3x y prime plus 3y minus 4y y prime equals 0. And we want to go ahead and factor the y primes out of the 2 terms that they're in. So that would give me y prime times 3x minus 4y. And at the same time, I'm going to move the 3y and the 1 from the sorry, my parenthesis was distracting me for a second. I was like, did I write a 1 there, or what was I supposed? I just didn't write my parenthesis very well. And so I'm going to move the 3y and the 1 over, so that'll be negative 1 minus 3y to be equal to the y prime stuff on the left. So now divide, and I'm going to say y prime is equal to negative 1 minus 3y over 3x minus 4y. And again, this is where we would stop for a lot of it. If you wanted to, you could kind of multiply everything by a negative 1 if you wanted the numerator to be more positive, but it'll work out to be the same either way. So we're evaluating this in terms of the point 1, 1. So negative 1 minus 3 times 1, 1, not negative 1. And in the denominator, 3 times 1 minus 4 times 1, giving you, in the numerator, negative 1 minus 3 is going to be a negative 4. And in the denominator, 3 minus 4 will be a negative 1. So that means that y prime is equal to a positive 4. Now here, on this example, this one I am going to not just say you probably should. I do want you to go ahead and try pausing this particular problem and working it out in advance just to see it. Yes, it is a slightly more challenging problem than the one that we just did, but it's still very similar. It's still very doable. And in this case, we're not doing any substitution. We're just trying to isolate y prime. So see if you can go ahead and work this one out. Pause the video, work it out, and then hit play and see what I have when you put the work back up, or when the work pops up, and see how you did. Okay, how did you do? I got y prime to be 2x divided by 3y squared plus 10y minus 5. We have to use the chain rule on all of the y terms, really all of the y terms, but it really is obvious when the exponent is greater than 1. So the derivative of the first part using the chain rule would be 3y squared times y prime, or dy dx. The second term becomes 10y times y prime. The last y value becomes negative 5y prime. And of course, the derivative of the negative x squared becomes negative 2x with just the power rule. The derivative of the constant, of course, 0. Factoring out y prime of the 3 terms on the left and moving the 2x term away gives me the y prime times the 3y squared plus 10y minus 5 to be equal to the 2x, and then finally divide, and you're done. So hopefully you did okay with it. All right, let's move on here. Now this one here is when we're starting to integrate kind of a transcendental idea, the concept of the exponents, especially e to the x expression. So here it may or may not be super obvious, but on this bit here, we are using the product rule to evaluate this. So the derivative, leaving the first part alone, I would just get y. The derivative of e to the x is e to the x. So the next part, we, take the derivative of y. So the e to the x stays the same, and we take the derivative of y, which would be y prime. And on the right side, 3 pi, remember pi is just a number, so 3 pi is a constant. The derivative of the constant is 0. So isolate y prime, I'm going to get e to the x times y prime will be equal to negative y times e to the x. And then finally y prime would be equal to negative y times e to the x over e to the x, and you're going to see that those are going to simplify. So y prime is equal to negative y in this case. Here again, we're looking at the incorporation of other, derivative techniques with what we've seen before. For the cosine of xy, we're going to not only have to use the chain rule, but the product rule inside of it. And then, of course, we have something that we're going to differentiate on the right side. So the derivative, so on this bit here, we're going to use the chain rule and the product rule. The product rule is going to be the stuff on the inside, and the chain rule is just going to be the whole thing. So the derivative of the whole thing will be negative sine xy. The derivative of the inside part, we have to do the chain rule, so that's going to be x times y prime plus 1y. And on the right side, the derivative of x is 1, and the derivative of 3y will be plus 3y prime. So if you notice, we have the variable that we're trying to solve, the y prime. It's kind of inside of the parentheses here, and I did my parentheses in brackets, but we have to get that y prime out. So what I'm going to do now is I'm going to take the value of the negative sign, and I'm going to distribute it into the parentheses to get rid of that. So that'll be, in this case, x, or negative x times the sine of xy plus, nope, let me back that up a little bit because I'm missing my y prime. So that'll be negative x y prime times the sine of xy minus y times the sine of xy to be equal to 1 plus 3y prime. So now we have the y prime terms on two sides of the equal sign. So we need to isolate them on one side. So I'm going to have negative x y prime times the sine of xy. Bring the 3y over through subtraction, and it'll be minus 3y prime. Move the negative y sine xy to the right side, and that will give me equals 1 plus, oops, I forgot my y. y sine of xy. And now we can factor out the y prime term. So y prime will give me a negative x sine xy minus 3 to be equal to 1 plus y sine xy. So I hope you're starting to see why I like to use y prime, because if we had to write a bunch of dy dx's here, uh, we're already having to rewrite a lot of things anyway, and that would just make things really more complicated than they needed to be. So finally divide, and we're going to get y prime, or dy dx, to be equal to 1 plus y sine xy divided by negative x times sine xy minus 3. That's the prettiest looking answer I think I've ever seen. If you can't tell, that's sarcasm right there. So hopefully we're doing okay with this stuff. Again, pause it, rewind it, watch it as many times as you need to. On the next one, again, you're going to recognize here, not so much the product rule being put into play with the xy for the natural log, but really more that we can use the properties of logarithms to separate the logarithm into two terms. So this natural log of xy can be broken up into natural log of x plus natural log of y with the properties of logarithms to be equal to sine of x. So haven't taken the derivative of anything yet. We just have broken up the equation in using the properties of logarithms to try to help us isolate what the y prime is going to be. So the derivative of the logarithm in this case is going to be 1 over x plus 1 over y times y prime. Or if you want to, you could actually write that as y prime over y, but I don't want to, make it look too much like it should simplify to be 1. And on the right side, we don't have to worry about the chain rule because it's just sine of x, so the derivative of sine of x will give me cosine of x. And now I think you can take over from here as far as the algebra that we have to do to get y by itself. So here I'm going to say 1 over y times y prime will be equal to cosine of x minus 1 over x. And finally multiply everything by y to get y prime by itself. So that will give me y times cosine of x minus 1 over x for my final expression. And I don't see any reason to distribute that y. If you want to, you're welcome to, but I'm going to just stop there for that one. So far what we've seen is, first of all, how you do implicit differentiation with y, incorporating things like the product rule and of course the chain rule. How we're including some of our transcendental differentiation with logarithms, exponents, trig stuff as well. Now we're going to be looking at a little bit more of an application. So here it's asking you find the equation of a tangent line for the ellipse that we have here at the point -1 and +2. So at this point, I think everybody should be capable, if you've understood what I've explained so far, should be able to take the implicit differentiation of the equation that's given to you, evaluate the dy dx for the given numbers that we have, so that way you could find the slope of the line at that point and then be able to write the equation of the tangent line, ideally. So if you feel up to it, pause the video, work it out on your own, then hit play. Otherwise, just follow along with the explanation as I work it out. So let's go to a different color here because I keep using blue. Let's see, what haven't I used for a while? Let's try this, I don't know, orangey color here. So start by taking the derivative of the function as it's given to you. So the power rule on the x squared term will give me 2x. The chain rule has to be applied for the, I'm sorry, not the chain rule, but the product rule has to be applied for the x times y. So that'll be x times y prime plus 1y. And the chain rule is very much implied with the y squared term. So that'll be plus 2y times y prime to be equal to the derivative of 7, which is 0. Now, this is probably where, if you make a mistake, that's probably where it's going to be, is neglecting the negative sign there. The negative is going to be applied to the entire product rule derivative. So let's just go ahead and distribute that so that way, because we're going to have to do it anyway to get y prime by itself. So here I'm going to say 2x minus x times y prime minus 1y plus 2y times y prime is equal to 0. Now once I have that, this is where I do want to try to get the y prime terms by itself. So I'm going to factor them out of the two terms that we have. So factor out y prime of the first term, and that'll give me a negative x plus a 2y. And simultaneously, I'm going to take the non-y prime terms, and I'm going to move them to the right side of the equal sign. So in this case, I'm going to write it as y, minus y minus 2x, like that. Just so that way I can have my leading value to be a positive. If you want to write it as negative x plus y, that's fine. And then finally divide, and I'm going to say y prime would be equal to y minus 2x divided by, we'll keep the same thing, I guess. We'll just turn it around and say 2y minus x. Okay? So that is the expression for the derivative. Now we want to know what is the value of the derivative at the given point. So y prime, when we plug in the values that they gave us, so we have 2 minus 2 times negative 1 divided by 2 times 2 minus negative 1. So in the numerator, we're going to get 2 plus 2, so that's going to give me a 4, and 4 plus a 1 will give me a 5, so that would be the equation of the, or that would be the slope, essentially, of the tangent line at the point negative 1 and 2. So since they gave us those points, we're going to just plug those in, and it wants to know what is the equation of the tangent line. So the equation of the tangent line would be y, or f of x, whatever you want to use, is equal to 4/5 x plus 1 plus 2. And if you wanted to, I think this is the correct graph. Negative 1 and 2 is here. So from there, 1, 2, 3, 4, maybe about like that. Can I get it? Can I get it? Can I get it? Something like that. There would be the slope of the tangent line. And I think we can go from there. Let's see. And I believe, there we go. Yeah, the next one says find the equation of the normal line. So remember, normal means the perpendicular line. So opposite reciprocals in this case is going to give me negative 5/4 times x plus 1 plus 2. And if you want to write the perpendicular line on there, go for it. But let's see if we can finish this here. Now the next ones are going to start getting a little more interesting. because this next one especially is where we're getting into a higher order implicit differentiation where we're doing like a second derivative. I don't, don't quote me on it, but I don't anticipate you seeing much in the way of like a second order derivative with implicit differentiation on your AP exam. But is it possible? Maybe. I wouldn't say it's out of the realm of possibility. I would say it's improbable, but not impossible. So here, find the second derivative of the given function, cosine of y is equal to x. Well, the first derivative is going to be pretty okay, I think, if you've been following along with what we've been doing so far. So let's say the first derivative in blue. Okay, so the first derivative we have cosine of y is equal to x. So the derivative of the function at this point would be the cosine of the whole thing on the left would be negative sine of y, and the derivative of the inside part would give me my y prime, and the derivative of the right side is 1. So here is the first derivative. Okay, but we want to get it in terms of y. So let's get y, or I'm sorry, get y prime by itself. So y prime would be negative 1 over sine of y. There we go. Or if you prefer, we could write it as negative, oops, I got a dot there, I don't want you to confuse anybody. Negative times the sine of y inverse, because, or not inverse, but reciprocal. And so that's how we are going to look at it. And the reason why I go through that extra step, because this one, the fact that it's not in fraction form, I think is probably going to just make it a little easier to do the second derivative of the function. So that's what we're going to be looking at here. So let's do the second derivative. And let's see, we haven't used red yet. So let's do the second derivative in red. Okay, so right now I have y prime is equal to negative sine of y to the negative 1 power. So now let's do the second derivative, y double prime. And here we're very much going to have to use the power rule, the chain rule, everything that we've been doing. So the derivative of the whole thing, the negative 1 exponent times the negative in front of the parentheses will give me a positive value. And so that will give me overall sine of y to the negative 2 power when I use the overall power rule on that expression. Now we do have to take the derivative of the inside part, which in this case is actually going to give us, a double chain rule effect. So the initial derivative of the inside, the derivative of sine, would be cosine of y. And the derivative of the whole thing, or I'm sorry, so let me just collect my thoughts here. Because like I said, the second derivatives can get a little tricky with implicit differentiation. So we take the derivative of the whole thing. Okay, and that's where I'm getting ahead of myself. Let's change this a little bit. I didn't do the derivative of the inside part. Okay, so I took the derivative of the whole thing, okay, and yes, the derivative of the whole thing, sine y to the negative 2 power, multiplied by the And the derivative of the n side will be cosine of y, oops, bracket, but it has to get multiplied by itself of negative sine y to the negative 1 power. And that's where things are starting to get a little wonky here. Okay, so at this point, looking at the values here, we have bases that are the same, so we can combine those bases. So that'll be negative sine y to the negative 3rd power times cosine of y. And of course, because the exponent is negative, we'll move that to the denominator. So y double prime is equal to cosine of y over negative, or the whole fraction is just negative now, sine y to the 3rd power. And I should probably put that in parentheses. Otherwise, I would say sine cubed y, but I think that works out okay. Now here's where, again, are we done? Kinda, sorta, but not really. Because guess what? We started with, and this again has to do with a lot of the cyclical nature of, the trig stuff. Cosine of y is equal to x. So I'm going to come here and I'm going to swap x for cosine of y. So I'm going to say x over negative sine of y cubed. And that's where we're going to stop on that one. So there is your second derivative of your function. Not super fun, but definitely doable. So we're almost done. And the second derivative of the implicit differentiation, like I said, it's not going to be a huge concept for you, but is it possible to do? Yes. Now in this case, this last example that we have, it's asking us to find where we're going to have horizontal or vertical tangent lines. And I don't think if I remember correctly, I don't think the graph that I have here on the presentation is exactly what you should have in your notes. I think the scale is off. I think it's kind of doubled. Like, here we should kind of be counting by 2. So like this would be 2, 4, 6, and so on. I think that's how it's kind of scaled on your actual notes if you're following along with the notes for this video. But find the points at which the graph of this particular ellipse has either a horizontal or a vertical tangent line. So first things first, based on what we've done so far, is can you take the derivative of the equation that you have? And I think we've already seen this one or something very similar to it. So let me pick a new color here. Let's do purple. So the function that we have, if I start taking the derivative of it, I'm going to get 2x plus xy prime plus y for the product rule of xy plus 2y y prime for the chain rule of the 2y or the y squared is equal to 0 because the derivative of the constant is 0. Again, we're going to factor out the y prime terms. So y prime will give me x plus 2y. And simultaneously, I'm going to move the non-y prime terms to the left side. So that'll be negative 2x minus y. And so y prime, in this case, is going to be negative 2x minus y divided by x plus 2y. So that's the expression of the derivative. Now, in this case, we're going to have to look at it in terms of having horizontal and vertical tangent lines, because that's what it's asking us to do. So here, we are going to need to recognize that I can have horizontal tangent lines whenever the derivative y prime is equal to 0. So let's see what we get if I plug in 0 for y prime. So I'm going to say 0 is equal to negative 2x minus y divided by x plus 2y. And let's see, there's not a ton that we can do here. If I try to solve it by multiplying, the 0 multiplied by the denominator is just going to ultimately give me 0 is equal to negative 2x minus y. So I could say that y is equal to negative 2x in this case. And that at the very least gives me something. I could take this and if I take this and I plug it into the original equation, we can get something that I think we could probably work with. So if I take, and I know you can't really see it, but the original equation, let me just go ahead and write it here. The original equation, because I don't want to keep sliding up and down on this one. The original equation was x squared plus x times y plus y squared is equal to 8. So now we have an expression, at least in terms of y, that we can plug into the original equation. So if I do that, I'm going to have x squared plus x times negative 2x plus negative 2x squared equals 8. And if I do this, this will at least give me some value of x that I can work with. So let's see what we wind up with here. This will be x squared minus 2x squared. And this will work out to be a positive 4x squared to be equal to 8. So 5 minus 2 looks like I'm going to have, oh, holy moly. Yep. There's a typo, and I just caught it looking at my notes. That's part of the reason why the scale is off on the graph. This is not 8, that's 27. Apologies for that, but it's not going to mess any of our work up until we get to this point here. So I want to change all of these 8s to 27s. There we go. I knew there was something off, and I was just not catching it. I knew the scale of the graph was off. But anyway, so this is going to give me 3x squared to be equal to 27, meaning that x squared is equal to a 9. So x, I should have something at a positive and a negative 3. So we should have some kind of a horizontal tangent line at a positive or a negative 3, but we need to evaluate it for a vertical tangent line also. So let's let's give myself some space here. So if I want to look at it for a vertical tangent line, I essentially want to do the same thing. I want to take the function that we had and see what we were working with here. So let's pick another color for the vertical tangent line. So the vertical tangent line, of course, is up and down vertical. So if we're doing it at a vertical tangent line, that's going to be where y does not exist. Oh, there's the bell saying period is over. So in this case, going back to what I had for my function, let me go ahead and write that down here. So we had y prime to be equal to negative 2x minus y over x plus 2y. So if I'm looking at a vertical line where, of course, y doesn't exist, then that means I need to be working with the denominator here. So I need to look at that where x, or where the denominator is set equal to 0. So let's go ahead and do that. So x plus 2y is equal to 0. And we'll do the same thing here. We're going to solve this in terms of y. So here I'm going to get y is equal to negative 1/2 x. And I'm going to do the same thing that I did for the horizontal tangent line, is I'm going to take this and I'm going to plug this into the original equation. And let's see what we wind up with. So let me see if I can slide it up here so we can see the original. No, not a ton of space here. Let me write the proper original equation here, which would be x squared plus xy plus y squared equaled 27. So let's see what we get now when I plug that into the original equation for y. So here I'm going to have x squared plus x times negative 1/2 x plus negative 1/2 x quantity squared is equal to 27. So this here, x squared minus 1/2 x squared, and this will work out to be a positive 1/4 x squared to be equal to 27. So 1 minus 1/2 is 1/2. 1/2 plus 1/4 is 3/4. So 3/4 x squared equals 27. And let's see, I need to break out the calculator here because I don't want to do 27 times 4 in my head. But 27 times 4 divided by 3 on the calculator, I'm getting x squared to be equal to 36. So here I'm going to have x positive negative 6. So I'm going to have horizontal tangent lines when x is equal to a positive and negative 3, and vertical tangent lines when x is equal to a positive and negative 6. So if we go back and we look at the scale, so if we look at positive and negative 3, so positive and negative 3 is about here, and that does look like I would have horizontal tangent lines at those points. And in this case, positive negative 6, when x is equal to positive negative 6, that would really be about here. And I think the scale on your paper is more accurate than what this is, but we're going to have vertical tangent lines here and here. So I think the scale on the graph is off at positive and negative 6, but that's where we would identify horizontal and vertical tangent lines for this particular function, this particular ellipse. So in this case, I would be looking here. This looks like it should be working out to be at about negative 3 and positive 6, where that tangent point is going to be. This one would look to be at about 6 and a negative 3. And again, I understand that the graph is scaled wrong here, so I apologize for that. This one would be at about 3 and a negative 6, and this point here would be at a negative 3 and a positive 6. So those are the points that we would have horizontal and vertical tangent lines on this particular ellipse. And that was a bugger. This one, I'm going to have to go back and fix this at some point. The graph being wrong and the constant value of the equation not being right. But the process is good. So I hope the fact that the scale and the number being wrong didn't throw you off too much, especially if you're following along with your notes. But that is going to wrap it up for what we have with implicit differentiation. So if you have any questions about anything, ladies and gentlemen, please get in touch with me. I'll be happy to answer any questions that you have. And until I see you in class again, thanks for watching. Take care. I hope you're doing well. And we'll see you in class soon.